I will now talk about the notion of sequences and summations. And this is a short lecture relatively to talk about how do we sum the terms in a sequence. And this is a very important tool in many domains, but in our case in particular, when we talk about algorithms, which we will be talking about, when we talk about algorithms and we want to analyze how long they take, how many steps do they perform, sometimes we encounter sequences that we have to figure out what's the sum of the elements in these sequences, because that sum is the number of steps that the algorithm would take. So, for example, if you might see a program or an algorithm that has for I equal 0 to n, and nested inside it you have for j equals 0 to I, do something, okay? These two nested loops, how long do they take combined? Okay, so if this something here is, let's say, print hello world, okay? How many times does this algorithm print hello world? So if you look at this, when I is 0, the inner loop is going to execute once. When I is 1, the inner loop is going to execute twice. When I is 2, the inner loop is going to execute 3 times. So the number of times this program or this algorithm prints hello world is the sum from I equals 0 to n of I plus 1. Okay, because when I is 0, it prints 1. When I is 1, it prints 2. This is why it's I plus 1, not I. So the question is that what is this? Okay, what's this value in terms of n? And this is what this lecture is about. How do we find this sum here? Okay, and these sequences sometimes are like this, what we call arithmetic sequences. Sometimes they could be geometric sequences, and I will talk about 2 general techniques for solving them or finding these summations. Okay, so a sequence is a function from a subset of the set of integers to a set S. What do I mean by a function from a subset of the set of integers? What I really mean is we want to list the elements of the set S in some sort of order, right? Because the integers it's a well-ordered set, we have a total order on it. Basically, I want to give the elements of S in some order. And the first element, the second element, the third element, based on that order, this is what the sequence is. We have the notation A sub n here. A sub n denotes the nth term in the sequence. So A sub 1 is the first element. A sub 10 is the 10th element. Notice this notation here when we talk about when we use the curly braces A sub n. This notation is saying it is the sequence that's defined by A sub n. Okay, so this notation, the curly braces, is talking about the entire sequence of elements. Okay, so to give some examples of arithmetic of some sequences, for example, I can define as follows. I can say that the nth element of the sequence will always be 1. So what is this sequence? What's the sequence whose nth element is defined by 1? The first element is 1, the second is 1, the third is 1, the fourth is 1, and so on. So this is the sequence AN. Okay, it's basically all ones. Suppose I have A to the AN is n. The nth element is the value n. Then the first element is 1, the second is 2, the third is 3, the fourth is 4, and so on. Again, this is A sub n. I can define A sub n to be 1 over n squared. So the first one will be 1 over 1 squared. The second will be 1 over 2 squared. The third will be 1 over 3 squared. The fourth will be 1 over 4 squared, and so on. Okay? Of course, I can define whatever I want here. I can say that the nth element is n squared minus 2n plus 9. Okay? So what is the first element here? So A1 will be 1 squared minus 2 times 1 plus 9. Okay? So 1 minus 2 is minus 1 plus 9 is 8. We can go to A second, 2 squared minus 2 times 2 plus 9. 2 squared is 4, minus 4 is 0, plus 9 is 9, and so on. Okay, so you can define any sequence you want. We have two important sequences that we usually encounter. One is the geometric, one is the arithmetic. The geometric is a sequence of the form a, ar squared, and so on. So if you look at it, the jth element, the jth or the nth element in the geometric sequence, an itself is a r to the n. And if you look at an minus 1, it is a r to the n minus 1. So if you take an divided by an minus 1, it is a r to the n, a r to the n minus 1, which gives us r. Okay, so the geometric sequence, progression or sequence, is defined by the fact that every number is a constant times the number before it. Okay, the r is the same across this progression. So the second is r times the first. The 10th is r times the 9th element, and so on. Okay, we call a the initial element or the initial term, this a here, it's the first term in the sequence, and r is the ratio. Again, why it's the ratio? Because I'm taking an over an minus 1 gives me r. Okay, so r is the common ratio. So if you take a to be 2 and take r to be 3, for example, so the first element will be 2. The second is 2 times 3, which is 6. The third is 2 times 3 squared, which would be 9. R 3 squared is 9 times 2 is 18. The fourth one is a r to the third. Sorry. So the first one is a, the second is ar, which is 6. The third is ar squared, which is 18. The fourth would be ar cubed, so a 2 times 27, which will be 54, and so on. Okay, so this one here is a geometric progression. Okay. Arithmetic progression, the jth element differs from the j minus 1th element by an additive term, an additive constant, which we call d, the common difference here. Okay, so the arithmetic progression is defined by a plus d, a plus 2d, and so on. So if you look at an, it is a plus nd. If you look at an minus 1, it is a plus n minus 1d. And if you subtract them, you will get a plus nd minus a plus n minus 1d. And what you get from this is d. Okay, so this is why we call this the difference in this case, d, the difference. And again, here if you take, for example, a to be 2 and d to be 5, then what do you get? The first element is 2, is the a. The second one is 2 plus d, which is 7. The third one is a plus 2d, which will be 12. Then a plus 3d will be 17, and so on. So the difference is always 5, so you can add 5 to each one of these and continue, right? So the difference between any two subsequent elements is 5. So this is an arithmetic progression. One concept that we are going to encounter in this course is the notion of recurrence relation. And the recurrence relation is a sequence where the term is expressed in terms of one or more of the previous terms. So think about recursive algorithms where the algorithm or the function makes a call to itself with some other parameters, right? So we have, for example, Fibonacci series, where I talk about the sum of the nth element is the sum of the two previous elements, the an plus an minus 1 plus an minus 2. So this will be a definition of the Fibonacci series. And of course, we have to give here the initial condition. So for example, I can define a1 to be 1, a2 to be 1. Then the an is defined for n equal 3, 4, and so on. So this is a recurrence, this is what we call a recurrence relation, where the term an is defined in terms of terms that came before it, an minus 1 and an minus 2 in this case. Okay, so one interesting thing for us would be, what is the solution for something like this? So if I give you a Fibonacci series, what is a sub n in terms of n, for example? Okay, so this is what we mean by solution to the recurrence relation. Okay, so here in this case, I will just go with a simple case here because we will talk about recurrences later. If I have a0 is 2 and an is 2 an minus 1. So this is a recurrence relation. Okay, this is a recurrence relation. So the first thing you should do when you see a recurrence relation, try to write a few of the elements in the sequence explicitly. So the first element would be 2, the second will be 4, the third will be 8, then 16, 32. You will immediately see a pattern here. So a0 here, if a0 is 2, a1 is 4, a2 is 8, and so on. So you see that this is 2 to the 1, 2 to the second, 2 to the third, and so on. So an would be 2 to the n plus 1. Okay, this is what I mean by solution. That the nth term is 2 to the n plus 1. So it's really a value in terms of n itself, not in terms of an minus 1 and an minus 2 and so on. Okay. One of the things, as I said at the very beginning here, is that what usually we would be interested in with these kind of sequences is the summation of terms in these sequences. Okay, so an algorithm will have some sequence of operations in it. These nested loops and so on will give us a sequence of terms, but we usually would be interested in the sum of these terms. In general, we could be interested in 3 types of sums. One of them is, which doesn't usually arise much in the analysis of algorithms themselves, but one of them is the infinite series here, or infinite sum, where we sum from 0 all the way to infinity. So what's the sum of a0 plus a1 plus a2, all the way to infinity. Another one is, it's a finite sum from I to j. Okay, so here we are talking about ai plus 1 plus all the way to j. Okay, so we assume here that, for example, j is greater than I. Another one where we talk about a sub n, the sum of a sub n, for n that is an element of a set. So we are talking here about the sum of an for n that satisfy a certain constraint. So for example, I can talk about, the set of n is odd. Okay, and an. So what this means, if you look at this, a sub n such that the n goes over the odd elements, we are talking about a1 plus a3 plus a5 and so on. Okay, so we have usually these summations, and we are interested in finding their values for specific sequences. Okay, so the sum of the sequences yield a series. So Sn here, this series, is going to be defined by the sum of the first n elements. So S1 is just A1. S1 is just A1. S2 is A1 plus A2. S3, A1 plus A2 plus A3, and so on. Okay? So we would be interested in finding this series. Okay, so the S1, S2, S3, and so on. This is, now we have a series defined by these terms, or by these summations, and we are interested in finding a formula and a solution for the general S sub n. Okay, sometimes we sum from 0. Okay, sometimes we are interested in the summation from 0, sometimes from 1. There's not much really difference between them. If you know how to calculate the sum from 1 to n, but someone is interested in the sum from 0 to n, you just add a0. If you have calculated the sum from 0 to n, but we are interested in the sum from 1 to n, you subtract a0 from that sum. So there's not much difference really between these two. Okay, so here I will talk about two general techniques that are applicable for summation of series that arise from arithmetic sequences and from geometric sequences or progressions. Okay, So the first tool that is applicable for series that arise from arithmetic progressions is what we call the telescoping sum. Telescoping sum is a very simple equation or formula here. Imagine or series. Imagine that I'm interested in the series Sn, the element Sn in a series, and that Sn is the sum from j equal 1 to n of aj minus 1. Okay, so if you open up this sum here, you will see that when j is 1, this term here is a1 minus a0. When j is 2, it is a2 minus a1. When j is 3, it is a3 minus a2, and so on. If you look at this sum here, you will notice that the a1 and minus a1 will cancel out. You will see that a2 and the minus a2 will cancel out, and so on. At the end, all the way to, you will see that the an minus 2 would have cancelled out already. The an minus 1 and an minus 1 would have cancelled out. What we are left with is the an and the minus a0. So this whole sum, it's a sum of n terms where the jth term is aj minus 1 is really just an minus a0. Okay, so if we are interested in the sum in a series that arises from the sum of arithmetic sequences, the telescoping sum is one tool to use for that, and I will illustrate it with the series that arises from the general arithmetic progression. Okay, so we have this. I'm interested in the sum of the first n plus 1 terms from j0 to n of the elements in an arithmetic progression. So if you look at this sum, the first thing to notice here when you are doing summation like this, first of all, this is the jth term. Okay, it's a plus d times g. So the first thing to do with this is that we know that a has nothing to do with g. A is not indexed, so we can say that this is the sum of a from j equals 0, we can, to n. So we can break it into two sums. And the sum from j equals 0 to n of dj. Now, the first term here, we are saying add a plus n plus 1 times, right? So we are adding a plus a n plus 1 times. Why is it n plus 1? Because j from 0 to n. So this gives us a plus a n plus 1 times, it says a times n plus 1. The second thing is, since the second term is the summation of dj, so it's d times 0 plus d times 1 plus d times 2 plus d times 3. I can get d outside the summation, and I can make it like this. Okay? So I'm making progress here in terms of getting to a sum that is in terms of a and d and n. Okay? So I've already got here, I got to the d. The only thing that I need to evaluate is the sum of j from j equals 0 to n. Okay, so now I really need to calculate the sum from j equals 0 to n of j, and I would like to use the telescoping sum for this. Now, telescoping sum, I want to remind you that telescoping sum says that we need to be looking at the sum of aj minus 1 from j equal 1 to n, and this will give us an minus a0. So when you want to apply the telescoping sum, you really need to say what is aj, what is a sub j. Once you say what that term is, then you know what aj sub minus 1 is. So here I will define aj to be j squared, and I will explain why. Okay, because this is very important, because if someone asks you to find the series that arises from the sum of j cubed, you need to understand what is a j that you choose for that. Okay, so I want to choose a j to be j squared. So now, under the telescoping sum, the j squared minus j minus 1 squared, this is the 8j minus 1 from j equal 1 to n, would be a sub n. A sub n would be n squared, and the 0, a0, is when j is 0, it is minus 0. Okay, so minus 0 here. Okay, so now look at the sum on the left here. So the sum on the left is j equal 1 to n. This is j squared minus, this is j squared minus 2j plus 1. And this would equal j squared, cancel out, minus 2j, this becomes 2j, and the minus 1 here. And this is from j equal 1 to n. And this would be, again, I can take the 2 outside the summation. So 2, the sum of j from j equal 1 to n, minus 1. Again, the summation is the minus 1 from 1 to n. Okay, so minus 1 plus minus 1 plus minus 1 n times. So this is minus n. Okay, so this summation here is this. But what did we say? That this summation here, the 2j, the sum 2 of j from 1 to n of j minus n is n squared. Again, I got the n squared from here, right? In other words, 2 times this summation equals n squared plus n. From here, we get that the summation of j from j equal 1 to n equals n squared plus n divided by 2. Okay, so this is what this summation is. So if I go back to this one, this equals a times n plus 1 plus d. The summation of j from 0 to n is n squared plus n divided by 2. Okay, again, this summation here I'm using from j equal 1, but if I add 0 to it, it just adds 0. So this is how I calculate this. Now, you see how I use the telescoping sum to find the sum of j from j equals 0 to n. Now I want to go back. Why did I choose aj equal j squared? And that's very important here. It happens because of this. Look what happened here. Notice that I will subtract aj minus 1. So I want terms to cancel out, and I stay with terms of the form that I'm interested in. I am interested in j, the sum of j. Therefore, I defined a sub j to be j squared, because when I take j squared minus j minus 1 squared, I know the squared is going to cancel out. I will be left with j. So using this rationale, if someone, for example, asks you to sum, j cubed from j equal 1 to from j equal 1 to n, you would want to use aj to be something like j to the 4th, because aj minus 1 will be j minus 1 to the 4th. And the first, when you subtract these terms, j to the 4th is going to go away. You will be left with a term that has j cubed, it will have j squared, it will have j, and so on. So using this technique, you already know what's the sum of j's. You can use the same thing to use to compute the sum of j squared, and so on. Okay, so this is how we would use the telescoping sum to find the series or the sum of terms from the arithmetic progression. When we talk about the series that arise from geometric progressions, another tool that we use for computing or calculating the series is what we call perturbation. Perturbation is similar to the telescoping sum here. We want to do something to the sum that we are after, but we want it to be in a form that takes us back to the summation we are interested in. And there's no definition for the perturbation method, so I want to illustrate it with an actual example here. So suppose I want to get this geometric series, or the series that arises from the sum of the first n plus 1 terms in a geometric sequence. So if you look at this summation here, the sum of j from j equals 0 to n of arj, one simple case, if r equals 1. If r equals 1, then this summation is really just the sum of a from j equals 0 to n. So we are summing a plus a plus a n plus 1 times, which would be a times n plus 1. Okay? Now the question is that what happens when r is not equal to 1? Okay? If r is not equal to 1, we cannot do this simple summation here. So what we have now is Sn equals a plus ar plus ar squared plus ar to the n. Now I will multiply both sides by r. Why r? Because it is the ratio in this geometric progression. Okay? So I want to multiply both sides by r. So this is r times Sn equal r times a plus ar plus ar squared plus ar to the n. What do I get from this? R Sn equal ar plus ar squared plus ar to the n plus ar to the n plus 1. Why did I do that? When you look at this, immediately you will see something that looks familiar on the right-hand side, which is this term here. If you look at this, does it look anything like Sn, S sub n? The answer is yes. If you look at S sub n here, it is almost S sub n, it's just that doesn't have the term a. So this really is Sn minus a, right? This immediately allows me to say that Rsn is S sub n minus a plus a r to the n plus 1. Now I can just simplify here Rsn plus s minus Sn, sorry. It's actually minus Sn equal a Rn plus 1 minus a. In other words, we have Sn times r minus 1 equals ar to the n plus 1 minus a. From this, I can keep Sn on the left, and I have a times r to the n plus 1 minus 1 divided by r minus 1. And I have the summation. Okay, so S sub n can be treated just as a variable. I can multiply things by it, I can subtract things from it, and so on. Now, I wanted the summation of the first line here. I multiply by r. Notice that multiplying by r here allowed me to see on the right-hand side a term that looks like S sub n. Again, plus minus a very small perturbation here, or small difference. If you multiplied by r squared, you could have also got, you would have missed the a and a sub and ar and ar squared and so on. So this would have caused a slight problem there in how to get to the right summation. So r is the right term here to multiply because I perturbed the sum, but I perturbed it very slightly so that I can get back to S sub n. And the last thing I want to talk about briefly is the infinite series, or that arise from infinite summations. And we don't usually deal much with these in analysis of algorithms or in computer science when we are dealing again with algorithms, because we don't want algorithms to loop forever, right? I mean, there's an algorithm where you have a loop that doesn't terminate is not an algorithm that we are interested in. So here we are talking about, for example, the sum of the infinite series from j equals 0 to infinity. Now, one thing to do here is, when we know that S sub n from j equals 0 to n of a or j, we just calculated that, and it is a r to the n plus 1 minus 1 divided by r minus 1. So this summation we are looking at really is, so the summation from j equals 0 to infinity of a or j is, basically we are talking about S sub n. This is S sub n as n goes to infinity. What is this value here? Right? So what this is here is when n goes to infinity, look at the very important assumption here that we are talking about the absolute value of r is smaller than 1. So this is a number that's smaller than 1. If you take number smaller than 1, let's say half, and you raise it to the power n or n plus 1, it doesn't matter, and you say what does this converge to as n goes to infinity? Half times half times half times half, and so on. What this do is that this goes to 0, right? So this one is going down to 0, and this becomes, the top one becomes a times minus 1 divided by r minus 1. Okay, so if we have a, it's basically, we can talk about it as a divided by 1 minus r. Okay, so this is the summation, the infinite series, the sum of the infinite series. This is usually one of the techniques that you want to do. When you have a summation from j0 to infinity, first find the sum from 0 to n, find that term, and then reason about it, what happens when n goes to infinity. And this is where calculus factors in. You have to know calculus. Sometimes you have to use derivatives, sometimes you have to use other tools from calculus to get at this summation. But when you have infinite series, you do it in two ways. First, reason about what is s sub n for a finite n, and then using your knowledge from calculus, say what happens when n goes to infinity. And this is what this series converges to. Now, that doesn't mean every infinite series is going to converge. You can easily write, we can write that, for example, the arithmetic progression. If I look at the series from that, and I say what happens with this sum as n goes to infinity, it doesn't converge, right? I mean, if we have 1, 2, 3, 4, 5, and if I look at the infinite summation from this, it's infinite as well, so it doesn't converge. For some of them, it converges, like here, it converges to a finite value, which is a over 1 minus r. Sometimes it doesn't. Okay, of course, here r cannot be 1, okay? And this is one of the important things. We use it twice here, that the fact that r is smaller than 1 allows me to say that r to the n plus 1 converges to 0, and r is smaller than 1 means r cannot be 1, which means 1 minus r is not 0. So this is a well-defined answer.